This conference will now be recorded.
So, very good evening. We started with the chapter Mechanical Properties of Solid, and in the first day, very first day, we had learned about what is called elastic body, inelastic body, or plastic body, what is stress, what is strain, etc. We had learned. So, today we'll start with Hooke's law, then we'll learn various or different modulus of elasticity, and if time permits, we'll go for we'll learn stress strain curve also. Otherwise, we'll learn that in the next class. So let us start with Hooke's law. So before we go for Hooke's law, let me just recap a bit about few terms which we had already learned in the last class. One is stress. What is stress? The stress is the internal restoring force. Internal internal restoring force. Restoring force per unit area. Per unit area of the deformed body, which this is actually restoring force. Stress is actually restoring force which arises inside the deformed body, and which helps the deformed body to restore its original shape and size. Okay, that is stress. And mathematically, stress can be written as force per unit cross sectional area. So it has dimension ml t to the power minus 2 into L to the power minus 2. So you get ml to the power minus 1 t to the power minus 2. So this is the dimension of stress, and unit you know it is having the unit of pressure Newton per meter square in SI system. So Newton per meter square is the unit. And you look one more important point to be noted, that stress is actually force per unit cross sectional area, but it is in general it is actually not a vector. It is not a vector. It is not a vector. Not a vector. Okay. Stress is not a vector quantity because we cannot define the direction of stress in a particular direction. That's why stress is a stress is not a vector quantity. Okay. All right. So we have learned about, we have just recapped about stress. Now we'll recap the term strain. What is strain? Actually, strain is defined as the change in dimension to the original dimension. I have written it in terms of dimension. Dimension can be length, volume, etc. Okay, so change in the dimension over original dimension. So this is the ratio. Strain is the ratio of change in the dimension to the original dimension. So it is actually a unitless quantity. As you can see, both are the dimensions, both are having the same dimension. So it is unitless quantity. It is unitless quantity. So stress and strain we have learned. Now, what is elastic limit? See, suppose I have a thin wire. I'm just putting a load on this, some 5 kg. Okay. So what will happen? Suppose the wire was having a length L in the beginning before I put the load. Now look, upon putting the load on this, its length has got changed. It has become L plus delta L, suppose. L plus delta L, where this is delta L. Okay. Now if you leave the or remove the weight, what will happen? This will go to the previous length. Okay. So when we put a load, the length of the wire increases. When we remove the load, it regains its original size and shape. Nice. Now, but if we just put on adding weight on weight on this thin wire, what will happen after certain amount of weight you put here and then remove them, you will look that the wire does not regain its original shape and size. That means, I'll repeat it. Suppose you have put a small load, then you are applying a sufficiently large load to the wire. Then after you remove this load, the length of the wire does not regain its original length. That means there is a permanent deformation. Now if you apply sufficiently large or sufficiently large amount of weight at the end of the wire. So in the beginning we had put lower amount of or least amount of load, then keep on increasing, and upon suspending a sufficiently large load, the wire become permanently deformed. It does not regain its original shape and size. So what does this indicate? That any material, it has a capacity to withstand certain amount of load. Okay, within which whatever load you may suspend and remove, it will regain its original shape and size completely. But beyond that particular load, it is permanently deformed. It cannot regain its original shape and size. So that is called the limit. So this is the limit. So if we define the limit, that is called elastic limit. So elastic limit may be defined. Elastic limit may be defined as the maximum stress. Okay, elastic limit may be defined. It is defined defined as the maximum stress. Maximum stress. Maximum stress within which within which the body completely regains completely regains its original shape and sizes size. Okay, upon removing the stress. So this is called the limit. Okay, the this maximum, so the maximum stress, it is defined as the maximum stress within which the body completely regains its original shape and size upon removing the stress is called limit, elastic limit of the body. Elastic limit. Elastic limit of the body. Okay, this is called elastic limit of the body. Now, if we apply stress to any body beyond its elastic limit, it will acquire a permanent deformation. Permanent deformation. And then the object is called overstrain. Overstrained. What is that? Overstrained. Now we'll learn. So these are the terms which are needed to define or to learn the Hooke's law. That's why I had uh, recapped this portion. Now, what is Hooke's law? Actually, Hooke's law states that Hooke's law states that Hooke's law states that within within the elastic limit, within the elastic limit, the stress is directly proportional to stress is directly proportional to the strain, directly proportional to the strain. Okay, this is Hooke's law. Within the elastic limit, the stress is directly proportional to the strain. Thus, within the elastic limit, I can write stress is stresses SS directly proportional to strain. Okay, stress is directly proportional to strain. That means if I write in terms of ratio, stress over strain will be a constant always. Okay, stress by strain will be a constant always. Okay, the constant of proportionality is called proportionality. Constant, this constant of proportionality this constant of proportionality is known as known as modulus of elasticity or coefficient of elasticity, known as modulus of elasticity or coefficient of elasticity. Okay, so we'll learn today this constant of proportionality or the modulus of elasticity or coefficients of elasticity. So there are different types of this constant of proportionality which are called modulus of elasticity. Now we'll learn what is modulus of elasticity. So I hope you have understood that Hooke's law states that within the elastic limit the stress is directly proportional to the strain, and if you write in terms of equation, stress by strain will be equal to a constant, and that constant of proportionality is known as coefficient of elasticity or modulus of elasticity. Now we'll learn what is modulus of elasticity. We have learned a little bit already. Now we'll recap what is modulus of elasticity in terms of definition. So modulus of elasticity is defined as the ratio of stress to the corresponding strain within the elastic limit. Okay, so modulus of elasticity or coefficient we have already learned from Hooke's law. This is proportional to constant. Okay, this is called elastic modulus of elasticity. Okay, now we had learned different types of stress and different types of strain also. Depending on that, there are different types of modulus. Now you have to understand this modulus of elasticity. Modulus of elasticity this modulus of elasticity is stress by strain, and this has a particular unit. So strain is dimensionless and stress has dimension. So you look, the modulus of elasticity will be having dimension as ml to the power minus 1 to the power minus 2. Okay, this is modulus of like unit of modulus of elasticity, and this is same for all the modulus of elasticity. So we'll discuss about various types of modulus of elasticity now. different types of moduli of elasticity. So we had already learned various types of stress and various type of strains also. Depending on those different types of stress and different types of strain, this modulus of elasticity or modulo of elasticity are of three types. One is Young's modulus, Young's modulus. Okay, Young's modulus or the modulus of or the modulus of elasticity of length. Okay, this is the one type. That means stress and strain. Basically, the strain produced by certain type of strain will actually contribute to will be contributing a certain category of elastic coefficient or modulus of elasticity. So when there is a change in the length or the strain is along the length direction or length along the length, then the coefficient of elasticity or modulo of elasticity is known as Young's modulus. We will discuss it further detail in the next slide. Then the second one is the bulk modulus, bulk modulus, and it is denoted by K. Young modulus is denoted by Y. Okay. So what is bulk modulus? Bulk modulus is actually elastic coefficient of or elastic modulus of volume, volumetric elastic coefficient. Okay, modulus of elasticity of volume, modulus of elasticity of volume. Okay, so we have seen volumetric change. So if we write down the coefficient of elasticity for volumetric change, then we can write bulk modulus K. It is given by K. We'll discuss in detail. Now, modulus of rigidity or shear modulus. Modulus of rigidity or shear modulus. This is related to shearing strain. Shear modulus or rigidity modulus or modulus of rigidity. Modulus of rigidity. Okay, so there are three types of modulus, and this rigidity modulus is denoted by eta. Eta. I'll discuss these things detail in the next few slides. So first, let us understand about Young's modulus of elasticity. So as I said, Young's modulus of elasticity is actually related to the change in the length. So within the elastic limit, when the length is changed, actually, then this modulus of elasticity, it is Y. It is written as stress by strain, right? Stress, longitudinal stress, longitudinal stress, longitudinal stress longitudinal stress by longitudinal strain. Okay, and it will be having dimension because this strain does not have any dimension. It will be the dimension of stress. So ml to the power minus 1 t to the power minus 2 for all the modulus of elasticity. Now, what is longitudinal stress or what is longitudinal strain? Suppose we have a small wire or rod. Here it is rod maybe, which has initial length L and area of cross section A. Now, if we just extend the length by applying a force along the line, along the direction of the length, if we apply the force, okay, force capital F, then stress will be longitudinal stress because we are applying the force along the direction of change in the length. The stress is longitudinal stress and it is given by F by A. F is the length and A is the area of cross section. What is longitudinal strain? See, upon applying this stress, how much is the change? We look here in the figure. What is the change in the length? That is delta L. So what will be the strain in this case? Longitudinal strain will be delta L by L. This is longitudinal strain. Okay. Now, if you want to calculate what is Young's modulus, then it is stress by strain. What is stress? Stress is this one. What is strain? Strain is a delta L by L. Okay, delta L by L. Now, if we solve for this, see, you will get F into L divided by A into delta L. Okay, so this is longitudinal stress and this is longitudinal strain. That means the change happens along the lines of the length of the rod. Okay, and as I said, it has unit Newton per meter square, and the dimension is ml L to the power minus 1 t to the power minus 2. Okay, so this was Young's modulus. Now, one thing, if since this wire is circular, then area of cross section can be written as pi r square. Pi r square. Okay, so in that case, you know what we can write Young's modulus if this is denoted by area of cross section. So F into divided by L delta L. So this A area has to be written pi r square. Okay, so this is the thing, and you look here from this particular modulus, we can define the force also. Okay, anyway, so this is the case. dl F into L by dl area is pi r square. Now we will learn about the other one, that is bulk modulus. What is bulk modulus? We have already discussed what is bulk modulus. Bulk modulus is actually, it is the ratio of volumetric stress to the volumetric strain, stress to the volumetric strain. Okay. So, all right. Before I move on to the bulk modulus, let me give you certain value of Young modulus. See, there are different materials, and depending on the materials, because they have different density, etc. So, different materials like aluminum, copper, iron, steel, glass, they have different values of various modulus, various moduli. Like in case of aluminum, Young modulus will be 70 into 10 to the power 9. And what is the unit? That is Newton per meter square. Okay. This will be the Young's modulus for aluminum. This is for aluminum. Let us see what is that value for steel. For steel, steel it is 200. For steel it is 200. 200 Newton per meter square. Okay. So if the Young modulus is more, then the object is more elastic. More elastic. Okay. If the Young's modulus is more, then the body is more elastic, and vice versa. Okay. So this is about Young's modulus. So Young's modulus has, see, this is the order. Generally we write Young modulus in terms of this order, 10 to the power. So this also has 10 to the power 9 meter per second square. Alright, this is Young's modulus. We will go to the bulk modulus. Bulk modulus actually is defined as the normal stress to the volumetric strain. We'll go to that and learn here. See, suppose there was initially a rectangular box. It has a volume V. Okay. Now, as you see, from all faces, on the all faces, if the pressure is given, then the block, this rectangular block, will have reduced volume. So volume has been removed here. Sorry, reduced here. Suppose the change in the volume is delta V. So here, this is the volume now for this one. Effective. So now see, if earlier it was V, so this will be the strain, volumetric strain. This is called volumetric strain. I'm sorry, this is actually uh, delta U, delta V. Delta V, if the V is the change, delta V is the change and V is the original. So this is the volumetric strain. Volumetric strain or volume strain. This is volumetric strain. So what is bulk modulus then? Within the elastic limit, the ratio of normal stress to the volumetric strain is called the bulk modulus. So what is that? Within the elastic limit, the ratio of within the elastic limit the ratio of normal stress normal stress to the volumetric strain volumetric strain. Now we'll see what is normal stress. This is the force per unit area of cross section that we know. So as I said, bulk modulus is denoted by K. So it is capital K actually, capital K. We should write in terms of capital K to denote the. So A by A will be the stress, normal stress, and strain will be delta V by V. Okay, delta V by V. Now look, this I can write as pressure. This I can write as pressure. So pressure into volume divided by change in the volume. So this is the bulk modulus. And you look here also the dimension remains the same. ml to the power minus 1 t to the power minus 2, and also the unit remains same, Newton per meter square in this case also. Okay, now one thing here is very clear that PV by delta V is the bulk modulus. Okay, so from here actually sometime you will be given a problem in various exam. What is compressibility? Compressibility compressibility is actually reciprocal of bulk modulus. Reciprocal of bulk modulus is compressibility, that is 1 by K. We'll write in the next page. So let us write compressibility. So it is the reciprocal of bulk modulus. We have to write the bulk modulus first, and then we will see what is compressibility. So we know bulk modulus is PV by delta V. Now this will become compressibility become del V by PV. Okay, so this will be compressibility. Okay, so in this case you look, in this case if we put the value of delta V, this generally becomes less. Okay, so this compressibility or this bulk modulus is written with a negative value. Okay, because this change when you apply pressure, you look, you are reducing the volume. So final to my initial volume is minus volume, minus of delta V. So this will be minus sign. So here in the compressibility also there will be a minus sign over here. Okay, compressibility, in the compressibility expression there will be obviously a minus sign. So delta V by P into V. Okay, this is compressibility. Oh, I'm sorry, compressibility is just reciprocal of that. P, yes, compressibility was all right. Compressibility was delta V by PV. Okay, this is the expression. This is the expression for the compressibility. Okay, and if you just take the ratio reverse, or if you inverse it, you will get K PV by delta V with a minus sign in the bulk modulus. Now we'll see what is rigidity modulus. Modulus of rigidity or rigidity modulus. Modulus of rigidity, or sometimes it is written rigidity modulus. So what is rigidity modulus? So we have seen that if you apply a force tangentially to the surface of any object, then the upper portion and lower portion, they will be little bit displaced from each other. Okay, that is called shearing stress, and modulus of rigidity is shearing stress to the shearing strain. Okay, look here, what is shearing stress and what is shearing strain and how to calculate, we'll write down here. The rigidity modulus first, let us see in the solid lines there was a rectangle. Okay, rectangle. Okay, now if you apply a force on this particular rectangular box, then the upper portion of this box will be getting displaced. It was, suppose earlier it was at A and B, the endpoints. Now the edges actually gets displaced by A prime, this much length, this is L, A prime is L, then B, this is B, gets displaced by B prime. Okay, so A gets displaced by A prime. This is the length, and same length is this one also. This one is also the same length, B prime. Okay, this B prime is also length L. And see here why this kind of displacement is happening for the upper portion, and what happens to the lower portion. Lower portion is actually fixed with the ground, and a force which is acting exactly opposite to the applied force on the upper face, and it is having the same magnitude. So these two forces in the fixed plane and the plane surface, top plane surface, these two will be actually displaced from each other because of this couple. So look, there is a surface like this, so there will be force, applied force in this way, and there will be another force which is arising at the bottom face, which is fixed to the ground, so that will not get displaced, but the other one gets displaced, and because of that, there will be shearing strain or twisting strain, shearing or twisting. And this shearing strain, look here, the shearing strain is, see, angular strain, if you just measure by angle, this is theta. Okay, this is theta. So you look, the actually the rigidity modulus written as eta. Eta can be written as tangential stress by shearing strain. Tangential tangential stress by shear strain. Okay, so tangential stress by shearing strain. Now let us see how to find out shearing stress and shearing strain. Tangential stress, anyway, tangential stress, this much, this is obvious that it will be F is equal F by A. What about shearing strain? Shearing strain is theta. This is shearing strain is theta actually, and that theta can be written since it is very small. We are just assuming, so theta will be nearly equal to tan theta, and tan theta will be C. This is a perpendicular by base. Uh, yes, base will be AD. So perpendicular is AA prime. Okay, so perpendicular divided by base. Base, you say this one, A into D. A into D or AB. Okay. A prime divided by AB. A prime divided by AB. This has the same length as AD also. So that's what we can write, AB. And this is again A prime. So delta L by L. Modulus of rigidity now we can write as C theta can be written as A by A by theta. Okay, so this is stress by strain. Now A by A by A, and what is theta? Theta is actually given by, see, theta is nearly equal to tan theta, that is given by delta L by L. Okay, delta L by L. So if we do little bit of simplification, we get F into L, A into delta L. Okay, so this is rigidity modulus. So what we have learned, rigidity modulus is actually arising when you have a object of rectangular shape, then you apply a tangential force on the top surface, the bottom face will be fixed with the ground, so there will be a couple, there will be a force in the bottom face also, which will be acting just exactly opposite to the bulk of the material or the upper portion, the force on the upper portion, and they will create a couple. That couple actually will help the object to have shearing strain. Okay, now shearing strain, rigidity modulus also has, like various materials have their different value of rigidity modulus. Okay, so I think I'll stop it here for today. This or let me write it once again clearly. This is tangential stress by shearing strain. So the shearing strain is given by theta nearly equal to tan theta. This can be written as A prime. This is the change in the length. Suppose here it is given as AL. I can write this as delta L divided by, suppose this is the AD. AD is the L. AD. So this is delta L by L. Okay, so this is what is the shearing strain. So eta will be tangential stress as this, and this is delta L by L, and hence F into L by dl into A. Okay, so this is what is called rigidity modulus, and various materials like aluminum, brass, copper, glass, iron, lead, nickel, these are the metals. They have different value of rigidity modulus. If you compare the value of rigidity modulus, actually aluminum has least, and then you have nickel and steel, even tungsten has the highest. Tungsten has the highest rigidity modulus. Okay, so we'll stop it here for today. We'll next day we'll learn in detail about the stress strain curve, and we'll take up few numerical example on various moduli. Okay, so I'll stop it here. Bye for today.